Okay, we're continuing with quiz review for 6.2, 6.3. So number 5, the rate of increase of a population, P, is directly proportional to the population at any given time. If it takes 5 years for the population to double, how long will it take the population to quadruple? And if the population is 10,000 after 3 years, what was the initial population? So the order pair that we're dealing with is independent is time, dependent is population. So we don't know the initial population. I'm just going to let C represent the initial population. So we know that based on the problem here, 5 years for the population to double. So 5 years, after 5 years, we know the population will be twice the initial population, so 2 times C. And how long will it take the population to quadruple? So if it takes 5 years for a population to double, then it should make sense that it'll take 10 years for the population to quadruple. So we don't have to do any much calculation there for this portion. And if the population is 10,000 after 3 years, what's the initial population? So we're trying to figure out, after we also have the information that after 10,000, after 3 years, population is 10,000. Okay, so let's see if we can create our differential equation. The rate of increase of population, so P, so rate of increase, so this is referring to P prime, is directly proportional, so P prime is equal to K times P. So that's our initial differential equation. This is P prime. We can rewrite it as dP over dt. Separate the variables. We get dP over P is equal to K dt. Take the integral of both sides. We get natural log of the absolute value of P is equal to KT plus C. Raise both sides with base E. We get P is equal to E to the KT times E to the C. Pull the C in front. So we have our general equation. This is going to be a little bit different. Usually we solve for C first, then we solve for K, but we're trying to solve for C as our final solution. So we actually need to go through and find K first so that we can find our C value. So in this problem, we have to do things backwards a bit. We have to solve for K first, okay, in order for us to get to C. So let's look at the information that's provided. We know that after 5 years, the population will double. So I'm going to let 2C represent my p-value and plug 5 in for time. Okay, so even though we don't have the C value, we can still solve for K. Here, conveniently, the C's canceled out, so we have 2 is equal to e to the 5K. We want to bring the 5K down, so we're going to introduce logs into the problem. So ln of 2 is equal to ln of e to the 5K. Bring the 5K down in front using log power property. The natural log of e cancels out, becomes 1. So we get 5K is equal to ln of 2. Divide both sides by 5, and we get K is equal to ln of 2 over 5. We have our K value. We have our, we are one step closer to solving for C. So P is equal to CE to the ln of 2 over 5 times T. Okay. Now, what we do have is we have this ordered pair to help us now plug in and solve for C. Okay. So 3, let's plug that in for time. 10,000, let's plug that in for P. So 10,000 is equal to CE to the ln of 2 over 5 times 3. So we can just plug all this in the calculator. This gives us 1.5157. Divide both sides by that value, and we get our C value is 6,597.539. Okay, let's look at number 6. Okay, so sugar decomposes in water at a rate proportional to the amount still unchanged. If there were 50 pounds of sugar present initially, okay, and at the end of 5 hours that's reduced to 20 pounds, how long will it take until 90% of the sugar decomposed? So our independent is, again, time. Dependent is sugar. So we know that at 0 hours, initially, 0 hours, there will be 50 pounds of sugar present. After 5 hours, there's only 20 pounds. And then how long will it take until 90% of the sugar is decomposed? So the way that this is worded is a little bit different. Rather than saying how long will it take before 10% of the sugar remains, it's saying the wording is saying 90% of the sugar disappears. So I'm using this 90% to figure out how much disappears and then subtracting that from the initial value. So 90% decomposed, so 0.9 of 50 will give me 90% of the sugar, so that's 45 pounds. So how long will it take before 45 pounds goes away? So if 45 pounds goes away, and if we start at 50, then 50 minus 45 is going to be 5. So when 90% is decomposed, there's only 5 pounds remaining. So the wording is a little bit, we have to kind of work around the wording, basically. It's not 45 that is going to be the value for sugar. It's going to be 5 pounds. So we're trying to find out how long before, how long will it be, how many hours will pass when only 5 pounds remains. Okay, sugar decomposes at a rate proportional. So we know that this is referring to S prime. So S prime is equal to K times S, the amount still unchanged, the amount remaining. So that is represented by S. Okay, differential equation, S prime, we're going to rewrite that as ds over dt. Separate the variables. Take the integral of both sides. So we get natural log of S, exponentiate both sides, so we can bring the S out from under the natural log function. Is equal to CE to the KT. Plug in the order pair 0 and 50, and we can solve for C. C is equal to 50. Once we have our C value, then we can solve for K. Plug the next order pair, 520. So 5 plugs in for time, 20 plugs in for S. And one step at a time, we're going to get to isolate this e to the 5k, so we can solve for k. Divide both sides by 50. 20 divided by 50 is 0.4. Take the natural log of both sides so that we can bring the 5k down from the position as an exponent. Once the 5k comes down, the natural log of e is just 1. So divide both sides by 5, and we get k is equal to ln of 0.4 divided by 5, or 1/5 times ln of 0.4. So we have our k value, we have our c value, now we have our specific equation. So once we have our specific equation, now we can solve and find how long it's going to take before 5 pounds remains. So 5 plugs in for time, 5 plugs in for S, for the amount of sugar, and we're going to solve for T. 5 divided by 50 is 0.1. And we can take the natural log of both sides, so we can bring this exponential expression down in front. Once we have that, then we get 1/5 natural log of 0.4t. We're going to solve for t, so multiply both sides by 5, divide both sides by natural log of 0.4. So here is our specific expression, specific value for time. And we can plug this in our calculator, and this equates to be roughly 12.565 hours. So it's going to take roughly 12 and a half hours will pass before 5 pounds of sugar remains.